Hey guys, welcome back to MindVenture. In this video for Discrete Math, we'll be covering simple proofs. We're not going to be looking at proof by recursion just yet. We'll be looking at that in the next few videos, and you can also check out the first video in this playlist for an example. But yeah, we're just going to be looking at the simple proofs, how to prove a basic level problem, and yeah. So before we get into that, what are proofs? Well, proofs are just, a way to show, a way to establish that a theory is correct, right? So again, if you recall from your logic courses, we have premises and then the conclusion, which follows the conditional statement. So if this, then this, right? So we already have the theorem if this, right? And now we have to prove the premise then this. Okay, so how do we do that? Well, first of all, we want to look into keywords. So what keywords should you use in a proof? And some of those are set, pick, and choose, right? So if you've already seen the first video in this playlist, I already use, a variety of these keywords to prove the theorem that is displayed. However, you don't necessarily have to use them unless it's required, but basically the way to prove it, as we've seen in the previous videos, depends on what type of quantifier you're using. If you're using a universal quantifier, and if you want to prove something to be true, it's going to be very different than if you're using an existential quantifier and you want to prove something true, for example. So, for full in-depth analysis of that, you might want to check out our quantifiers video, which is the last one. But yeah, we're going to assume you already checked that. So if you haven't, you might want to go check it out now. Anyways, we're going to be providing a case-by-case analysis of possible inputs and outputs for a proof. And also, always remember to end your proof with QED. Or you could use a shaded out square. That could also work. And then some other keywords that we forgot to mention also include let, then, as such, and then therefore, and so. So, now, once again, we can get started with the proof. The first example we're going to prove is a very basic example. Basically, we have a theorem right here for all integers. X is greater than or equal to 0. We have to prove that x to the 4 does not equal 125. Now, this statement is true. Right? Well, I'm already telling you that it's true. Now we just need to prove that it is true. Okay? In some questions, it will tell you explicitly that this statement is true or it is false. But the objective behind the question is to prove that it is true or false. So how do we write out a formal proof? Well, you want to start by labeling, of course, proof. And then you want to start, always, what I like to do is to number the lines so I can refer back to them in case, I want to refer to it in future lines. But yeah, we'll just start by saying, let's let x be an integer. Okay, so usually this, in many circumstances, may be your first line in a proof. In many circumstances, because you want to pick an arbitrary value from the premise that is being provided to you to prove the theorem that's being given to you. So we want to prove that x to the 4 is equal to 125. How do we do that? Well, one of the methods that comes to mind when I think of this problem is we should prove that every number from 0 to 3, every integer from 0 to 3 does not satisfy this quality, and then every number after 3, so 4 to infinity, doesn't satisfy this quality either. Because again, remember, this is a for-all proof in which we're proving the theorem to be true. So we're going to have to really satisfy every single case in the universe, but we can do that all at once, right? So let x be an integer, and we're going to look at the first case where let x be an integer satisfying 0 is less than or equal to x is less than or equal to 3. And then we're going to start with case 1. This is case 1, right? 0 is less than or equal to x less than or equal to 3. Line 2, then x to the 4 is less than or equal to 3 to the 4 because x is less than or equal to 3. X, not s. And then that also indicates that 81 is less than 125, which is correct. Because x to the 4 is 81 and 3 to the 4 is 81, and 3 is the highest number you can get between 0 to 3. And that is still less than the 125 we need. So we know that even x to the 4 could equal 125, we know that that number x is not between 0 and 3. So we'll move on to case 2, which is let x be greater than or equal to 4. Be an integer. And this is case 2. Sorry, I should put this out in brackets like that. Now, then x to the 4 is greater than or equal to 4 to the 4. Because x is greater than 4, or greater than or equal to 4. And again, you want to explicitly refer back to your old lines or the statements that you're deriving the lines from, because nobody wants incomplete proofs, and if you do this on an exam, you'll 100% lose marks for it. Now, obviously, this means that 256 is 4 to the 4, which is greater than 125. So any number less than 3 will be less than 125, and any number greater than 3, when you take the fourth power of it, will be greater than 125. Therefore, you cannot have a number satisfying this theorem, making this theorem false. So now we can conclude, since we have reached our conclusion. Thus, if x is less than or equal to 3, or x is greater than or equal to 4, this theorem cannot be satisfied. So the theorem proves false for all cases. And then of course always end that proof with the shaded out square. Alright, now let's move on to a different example. And in this example I'll change the color so you guys can see. In this example, let's say there exists an integer. Actually, let's go with the same example. There exists an integer x is greater than or equal to 0, such that x to the power of 4 equals 125. And of course, we know it's not exactly the same example, because this one said x does not equal 125, and this one said it is equal to 125. So we know obviously that this is going to be false, because there is no integer such that that integer to the power of 4 is equal to 125. Now, how do we prove a false premise? Well, one of the most optimal methods is something called proof by contradiction. So proof by contradiction is you assume the reverse of the premise to be true, and then you derive a contradiction from that premise, which just falsifies the entire theorem. So, we'll start, of course, by writing out that we're proving, and then, it's always courtesy to the reader in the heading to write proof by induction. Or proof by contradiction, sorry. So yeah, it's always courtesy to the reader to write out which type of proof you're writing. So, assume this statement I've made a pretty big mistake here. This last proof we did in the conclusion, the premise proves true, because it says x to the 4 cannot equal 125. Yeah, that was a mistake on my end. Sorry about that. But over here we have assume this statement is false, meaning an integer x can exist such that x to the 4, or an integer x can't exist such that x to the 4 equals 125. Okay. Now line number 2. Obviously, we know from the previous theorem, you can also refer to previous theorems like this. We know from theorem 1, so let's say this is theorem 1. That the statement in line 1 is true. Thus, the reverse of this statement is false. Thus, therefore, this premise is false. And then end of proof. Right, so there's many proofs like that. We can also go into another one. For example, we can prove, a for all true proof like we did in the previous example. Again, I'll switch colors. So for all integers x, if x is greater than or equal to 0, then x plus 2 is greater than or equal to 0. Now this is obvious, right? Because if you have a number x which is greater than or equal to 0, then that number plus 2 will obviously be greater than or equal to 0. But something so simple, how do you prove it? Like, if you're a beginner to simple proofs, you might not know how to immediately prove it. Well, to write a formal proof, again, very simple. You just say, let x be an integer. This is always how you start in a non-inductive proof. Let x be an integer such that x is greater than or equal to 0. Write out fully such that you don't make like short forms like I did. But yeah, let x be an integer such that x is greater than or equal to 0. Then x plus 2 is greater than or equal to x is greater than or equal to 0. Thus, x plus 2 is greater than or equal to 0. End of proof. Right, so this is very straightforward, very self-explanatory. And again, we don't need very complicated methods of proving these. Most proofs will be quite simple, but yeah, this was just a way to show, what simple proofs would be. Check out the part 2 to this video where we'll cover some more examples for simple proofs.